Okay, so the second group of the workshop, headed by Jeff and Jeff. I don't know which Jeff is up first. I think it's Jeff.
Thanks very much. Okay, so thank you very much all for coming, and welcome to the second half of the Workshop 2001 final presentations. So before we begin, I just wanted to thank a couple of people for their contributions to the workshop this year. First of all, I'd like to thank both Sanjeev Kundampur and Bill Byrne for what I think were just outstanding and fantastic contributions to both the workshop in general and technical advice for the things that we've been presenting. I think without their input, I don't think this workshop would have been a success. Secondly, I'd like to thank Fred Jelinek, who, while was here only for a few days, I think his spirit was definitely felt, and was basically a very strong positive influence on our results as well. Third, I'd like to thank some of the people who made this workshop a possibility, people such as Jim Bass, Charles Wayne, Jack Gottfried, and other people like Mike Lesk and Ephraim Glinert and Gary Strong and Kathleen Egan. All of them, I believe, helped to make this workshop a possibility. And finally, I don't know if he's here, but I wanted to thank Michael Picheni at IBM Research for his support, and he also helped to, in many ways, make this a reality. And, okay, now that that's out of the way, I can introduce everybody on our team. So we had, I think, an outstanding team this year. I think everyone was truly fantastic, and everyone's input was critical to the success that we had. In particular, I'd like to thank my colleague and co-leader and partner in graphical models crime, Jeff Zweig. I think his intelligence and carefulness and clarity made this workshop very fun and successful, and we ended up getting a lot of stuff out of it that we wouldn't have gotten otherwise. Secondly, I just want to go through everybody very quickly. Thomas Richardson, who contributed an enormous amount. Kirk Jackson, who was fantastic. And then some of the students, Karen Levesque, Peng Chu, Kareem Falali, Eva Holtz, Jerry Torres, and Eric Sandness. And finally, two other members, Bill Byrne and Yigal Granman, who, and everybody, again, I think were fantastic. So thank you all. And some of you are here, others of you are still preparing your presentation. So thank you in your absence. Okay, despite the daunting outline of this talk, I think there actually is some logical structure. So essentially, we're going to have main presentations for an hour and a half, given by myself, Jeff Zweig, and Thomas Richardson, who were the three senior members on the team. And then part two of the talk is going to be student presentations and followed up by discussion. And that will include both undergraduate student presentations for about 5 minutes each, and finally the three graduate student competition presentations. And these will be the final ones that are to be judged by the three panelists that we have in the audience. Okay, so let's get started. I thought it would be useful to give a summary of the accomplishments that went on during the 6 weeks of this workshop and beforehand. So what we've done is build and designed a brand new graphical model-based toolkit for large task problems such as speech recognition and other time series modeling. So like HDK, it's general, but unlike HDK, it's more general than just using hidden Markov models. During the workshop, we really stress tested it. And, this is brand new code. We want to emphasize that this is all brand new. We stress tested the toolkit on 3 speech corpora, some of which were pretty difficult. So these included the Aurora task. We'll be describing these in detail later in the talk. An IBM audiovisual task, and spine. We evaluated the toolkit using different acoustic features. So we didn't just use MFCCs. And we began improving the word error rates with the approach that we've been purporting will be useful to use along with graphical models, basically discriminative structure learning. And we believe that the results will show and will have provided some insight into our domain, into speech, and hopefully ultimately language processing. Okay, so some of the audience is very diverse and people have different backgrounds, so I thought we should spend a little bit of time on just some background on basically what graphical models are. So I like to think of them as basically a formal and abstract visual language for reasoning about families of probability distributions. And what a graph describes is basically a family of probability distributions set of conditional independence assumptions. And you might say, okay, so what is so special about conditional independence assumptions? What's special about it is that when you change these assumptions, the model family can have a dramatic change. And in fact, in the past, people have thought of different sets of conditional independence assumptions as completely separate, different algorithms, for which books have been written. But when considered under this one framework, the framework of graphical models, everything can be seen under the same umbrella. Secondly, graphical models provide for an efficient graphical sets of languages that allow us to do the problems that we want to do, namely decision-making, statistical decision-making. And they do it in a way that we do operations on graphs, and we basically get efficient inference working. So why should we be applying graphical models to automatic speech recognition, which is our main task and was our main task for the workshop? Well, one reason is that it's very easy to quickly communicate amongst colleagues new ideas about probability distributions. For example, I can write down a graph and say, hey, Fred, what do you think of this model? And Fred will say, I don't like that model because you've got an arrow coming from here to here. Basically, you can very quickly understand what it is that we're talking about, and which otherwise you would have to have pages of equations possibly to describe and go through and actually understand. So it's just a cognitively different set of things that we can use to reason about these models that we want to try to use. Secondly, with the right computationally efficient and general tools, which we actually have now, we can say, all right, now that we've got a graph that we like, let's try it out. Okay? Let's get it working and see how it works. And that can be done in, let's say, minutes or days rather than weeks or months or maybe even years. Thirdly, graph structure learning can tell us something more than just the parameters of a fixed model. An HMM is a fixed model, and you train the parameters, and it's not clear necessarily what that model is telling us about speech or language. With a graph, if we do structure learning, the graph can tell us some high-level concepts about the domain. Next, there are potentially novel acoustic features can be customized. We can customize our model to match novel acoustic features. And I'll have a slide on that point a little bit later. So one of the things that the workshop was all about was this idea of structural discriminability. So we'll talk a little bit about that later on. But the basic idea, just to get you a flavor of what's going on now, is that we want to improve recognition while concentrating on that which is most important. Okay? And finally, again, the resulting discriminative structures can help us obtain new domain knowledge. Okay? In a sense, I mean, a hidden Markov model is one instance of a graphical model. So this is a graph which describes essentially all of the statistically important assumptions about the hidden Markov model, which is the model that, of course, everyone knows is used pretty much predominantly for speech recognition. But it's only one example in this large space of graphical models. And I think that one way of looking at it is the following, in terms of the set of features and hidden Markov models and MFCCs, is the following. So we have, think about this plane, actually, do we have the pointer?
It's on there.
It's on there, okay. Okay. So this plane here, think of it as a hidden Markov model. And hidden Markov model likes to see speech that fits nicely into this hole right here. And we spent the past 20 years developing MFCCs that fit perfectly into this HMM hole. Okay? One of the problems with new features, we believe, is that if you have novel features, essentially what we're trying to do when we're trying novel features in a HMM is we're trying to fit a square peg into a round hole. And it might very well be the case that these novel features are extremely useful, but when used with hidden Markov models alone, they don't yield their full potential benefit. So the idea of structurally discriminative, data-driven, self-adjusting graphical models is that the whole is self-adjusting to whatever kind of features we actually might have. So let's say we have some features which present themselves in this very odd, structured way. We can adjust the model to perfectly fit, we believe, the features as best as possible and representing speech as represented by these sets of features. So that's one of the other reasons for using these things for speech. But here's the bottom line. Graphical models essentially occupy this huge space of probability models. It's interesting to note that pretty much all of speech recognition fits about right there. Okay. So with the ability to explore this space rapidly, and we believe that there's got to be some life out there somewhere that we can, maybe over here or over here, for which we can find a model that will work better than the hidden Markov models for speech. Okay. Okay, so that's sort of the motivating part about graphical models. And now we're going to get into a little bit of the assumptions and details behind this idea of discriminatively structuring one of these things and why that's an important thing. Okay. So what is it that we want to do? Okay. We want a model that doesn't have any extraneous information in it about speech in order to do our task. And our task is classification. You know, speech recognition says we've got some unknown utterance. We want to say, is it a hello or is it a goodbye? Or is it this sentence or is it that sentence? That's a classification task. So in some sense, we want our model to represent only those things, and as efficiently and accurately as possible, those things that are most important to make a distinction between two or a number of different phrases. And the idea of structural discriminability is to look at the structure of the graph and try to include only those things in the graph that will help us precisely for this classification task. Okay? So in a sense, you can think of it as saying, all right, each graph for each word should represent only the unique and distinct properties, or in this case, dependencies of each class, and essentially not represent those common dependencies and properties. Okay. So here's a visual example of what we mean by this. So let's suppose that we're interested in recognizing these two key-like objects. So we've got keys with round holes on the left and a horizontal bar, and keys with diagonal bars and a horizontal bar. So one way of designing a classifier that tries to recognize these things is to try to recognize basically round holes and horizontal bars and diagonal bars and horizontal bars. But in some sense that's redundant, because the thing that's telling you about the difference between class A and class B is not this horizontal bar, it's the round versus diagonal bar stuff. So instead, what we are trying to do, what we're striving for, is to produce models which represent only those distinct properties of the objects, and we strip out that stuff that is common between the objects, thereby making it such that we only recognize things that are unique to each object. So we reduce parameters, we simplify the structure, and hopefully even do better, all with fewer parameters, less memory, all this kind of stuff, all this good stuff that we want to do. Okay? Here's sort of another way of looking at it from a graph point of view. So the idea is here we have a set of 4 random variables. This one for class 1. You can think of it, this is class 1, so maybe this is the round key and this is the diagonal key. And in this case, for class 1, we have these edges between the graph. And in this case, for class 2, we have these edges. The idea of structural discriminability, and this isn't to suggest that this is what we do. We don't subtract edges. But the idea of structural discriminability is to remove the common edges, leaving only the distinct ones for each class. Okay? So we get a much simpler model with fewer parameters and all of that, like we were talking about. Okay, so realistically, how do we really define these structures? How do we produce them? We need some quantitative measure of the quality of an edge in a graph. And it can be shown that it is known for classification that we want to maximize the posterior probability of the class given a set of features. So you can show that choosing edges to maximize the expected posterior probability is equivalent to choosing edges which maximizes this difference between mutual information quantities. Okay? So what that basically results in is what we're calling the ear measure. EAR stands for explaining away residual because it refers to something in the graphical models community that actually occurs. But we don't need to get into this right now. But basically what this is saying is we want the mutual information between x and z given q minus just the mutual information between x and z. We want this thing to be large. And if we do that, then we're going to choose edges that will improve the posterior probability and thereby improve classification. Okay? And in this particular context, for speech recognition, we are looking at it to basically say, here's x, here's our class 2, q, and how do we choose z as an additional parent of x, which helps essentially this measure. Unfortunately, doing this thing while theoretically justifiable is actually intractable. So one of the things that Thomas Richardson is going to be talking about is ways that we've gone over, ways that we've evaluated to actually try to approximate this quantity as accurately as possible. Okay, so now I'm going to turn it over to Jeff Swide. All right,
thank you. All right, so as I'm sure you're all familiar with, there's a large body of information that's associated with hidden Markov models, and people have a lot of experience working with hidden Markov models. And what I want to do here is try to present the way that you can capture the same kinds of things that you do normally in a hidden Markov model, with a hidden Markov model, in this new context, and then to point out some of the ways that you can actually use the graphical models framework to extend this, the previous things that we could do. The way I'm going to do that is first say a few words about the relationship between hidden Markov models and graphical models, the way you should think about that. In particular, when you reason about hidden Markov models, you typically reason about paths through a graph, and that is going to correspond in the graphical models context to reasoning about assignments of variables to the hidden variables in a graphical model. And then I'll be a little bit more precise and talk about some simple training structures, a bigram decoding structure, how to do training, for example, with optional silence, and finally some extensions. So here is an example of a simple hidden Markov model, and it's a little bit hard to read the letters, but this is a hidden Markov model for the word digit. It's d, I, j, I, t, and speech is recognized or generated by starting in a start state, proceeding to one of the states, perhaps cycling around in the state, and in each time frame emitting an acoustic observation. There are two probabilities associated with it. One of them, emission probabilities, the probability of an observation at a given time frame in a given state, and the other, transition probabilities, which label these arcs and aren't shown. Typically, the way you reason about these things is via paths through a hidden Markov model grid. Here's an example of a grid for a 7-frame utterance. So someone said digit, it took 7 frames, and one possible way of explaining that utterance is that you started, well, you have to start in d at the first time frame. Then at the second time frame, transitioned to stayed in the third time frame, went to j, I, t, and stayed in t. So you reason about the hidden Markov model in terms of these computational grids. It's a little bit different with the graphical model. Here the idea is to identify a set of variables that you're interested in each time frame and to keep track of that set of variables. You can emulate a sort of a very simple HMM structure that doesn't have any real constraints on it by keeping track of 2 variables, a hidden state variable and an observation variable. So those are these guys. At each time frame, we're keeping track of 2 variables, the hidden state and the observation. And it's also, the graphical model is very explicit about time. So if you have a 7-frame utterance, you have to have a 7-frame graphical model that repeats for 7 time frames. And that's what this model does here. And basically, the emission probabilities are captured in the conditional probability of the observation given the state, and the transition probabilities are captured in the probability of the state at time t given the state at time t minus 1. The path that's illustrated over here corresponds to this assignment of values to the variables. 1 frame in d, 2 in 1 in j, 1 in and 2 in t. And once again, this is relevant because when you see one of these model structures that's kind of complicated, and we're about to see one, what you want to think about is specific assignments of values to the variables. So the simplest possible training, let me go back one. Let me just say that this Markov model here, or this graphical model as it's drawn, has some problems. If you actually try to apply it to a training utterance, there are some constraints that are inherent in the training data that aren't captured by that model. In particular, for example, that you need to end in the final state of the graph. You could start in de, assign de, all the way down, plug in the conditional probabilities, get a number out. That number wouldn't be 0, but you know that that assignment of values to the variables doesn't correspond to an actual utterance of the word digit because it didn't end in the t. So there's a problem there. You need to give assignments of values to the variables that don't correspond to what you know in the training data, 0 probability, and this guy isn't doing it. The simplest way of setting up a model so that it does do it is to just keep track of the positions in the utterance. So in the word digit, there were 5 positions you could be in, and whether or not there's a transition at each point in time from one position to the next position. When you're in position 1, that maps to the phone de. When you're in position 2, that maps to the phone In position 2, maps to 3 to j, and so forth. And transitions are indicated by an explicit transition variable that's saying, is there a transition happening at this time frame, yes or no? And these are assigned values that are consistent with the values you see here. Starts out in time frame in state 1, it's a de, there's a transition, goes to position 2, it's an no transition, stays in 2, and so forth. You can capture the constraint that I mentioned before, that you end up in the final state, by putting an end of utterance observation over here that has an observed value of 1, and set the conditional probability of that so that the probability of seeing a 1 is 0 unless the position is 5. So then if you assign 1, 1, 1, 1, 1, 1, the whole thing gets 0 probability, which is what you wanted. If you set up a model, by the way, you can also condition this end of utterance on the final transition variable and insist that there's a transition out of the final frame at the end of the utterance. You may want to do that. If you set up a network like this, you can show that each assignment of values to the model corresponds to a path through the HMM. The sum over all the assignments is the same as the sum over HMM paths, and the max over variable assignments is the same as the maximum over HMM paths. This is useful for computing posterior state occupancy probabilities during training, and this one basically gives you a Viterbi decoding. So a somewhat more complicated structure is a bigram decoding structure. And let me just go through these variables. What we're really interested in is what was the word that the person was uttering at each time frame. So this is what we want. We want to, at the end of the day, find the likeliest assignment of values to all the variables, and then look at what the word variable, what that value is, and that'll say what the person said. But let's start at the bottom of the graph and work our way up. We've got the features, the observations down here. The observations are conditioned on the phone that the speaker is in at that particular time frame. The phone that the person is in is a function of the word that the person is saying and the position within the word. So for a word digit, the position could be 0, 1, 2, 3, or 4. At each time frame, there can be a transition to another phone, and this variable here is explicitly representing whether or not there's a transition. Okay, how do you figure out what word position you're in at a particular time frame? Well, let's suppose that you magically had some word transition variable that said whether or not there was a transition from the end of one word to the beginning of another word. You look up at the word transition variable. If there is a word transition, then you know that the word position at the next time frame must be 0. Once you transition out of a word, you have to go into the beginning of the next word. On the other hand, if the word transition value is 0, then you look over here at the phone transition, and if that's 0, no transitions at all, then you just copy the previous word position. Otherwise, you add 1 to the previous word position. You've gone, say, from the d to the in digit. All that kind of logic can be encoded in the conditional probability tables associated with the network. Okay, how can you tell if you have a word transition? Well, you look at the position within the word, and what word you're in, and you look up to see if you're in the final position. So you would be in the final position if the word was digit and the word position was 4. Then you would be in the final position. Then you look at the phone transition. If you're in the final position of the word, which you can determine from these two guys, and the phone transition is 1, then yes, there is a word transition. You were in the end of the word, and you saw a transition, and you moved on. Finally, the word at time t plus 1 is related to the word at time t by looking at what that previous word was and whether or not there's a transition, a word transition. If there's no word transition, then with probability 1, the word at time t is the same as the word at time t plus t minus 1. On the other hand, if there was a word transition, then the distribution over words at time t plus 1 is a bigram distribution given the history that's indicated by the assignment to this previous occurrence of the word variable. The one constraint that you want to satisfy in decoding is that you end up in the end of a word, and you can do that by, again, having an end of utterance variable that's an observation with the value observed to be 1, and the probability of seeing that 1 is 0 unless the word transition value is 1. So that's going to ensure that when you do the Viterbi decoding, you end up in the final state of a word. Okay, a slightly more complicated graph is a graph that you might use for training, where you know what the word sequence was, but you don't know whether or not there was silence between the words. This graph is the same as the graph that we saw before. It's the same as the bigram decoding graph, except that the link between words is removed, and there's a new layer up here, position in utterance. So this position in utterance variable is indicating, are you at the first word of the utterance, the second word of the utterance, the third word of the utterance? Where are you? Silence is also explicitly indicated. So 0 would be silence, 1 would be the first word, 2 would be an optional silence between the first and the second words, 3 would be the second word, and so forth. Okay, so since this is the only new thing, it's the only thing that we need to think about. And the position in the utterance, well, to figure out the position in the utterance at time t plus 1, you look at the word transition. If there is no word transition, you just copy the previous position. On the other hand, if there is a word position, then you look up here at this skip silence variable. There's some probability of inserting a silence, and there's some probability 1 minus that of skipping a silence. If skip silence is 1, you don't want any silence in there, then the position in the utterance increments by 2. It goes from the current word, skips over the silence, and gets the value of the next word. On the other hand, if skip silence is 0, no, you don't want to skip silence, then you increment the position in the utterance by 1, and you go from the word to the silences following it. Finally, there's this end of utterance over here that's insisting that you end in the final word of the training utterance on a transition out of that word.
So at that layer there is a word called silence, and the transcription has word silence, and we skip over that.
No, so this is for if the transcription doesn't have silence. If you just have the transcription, you don't know if silence should be in.
You just put that and convert it into a transcription, which forces the silence and then allows you to skip.
Yes, exactly. Right.
And then the pronunciation of that word silence in the phone called possibly silence.
Right, correct. Yes.
I want to make sure I'm understanding the notation. So you have the training transcription as with marker models.
Correct.
It has the sequence of words, each word appearing once.
Right.
And you know what the sequence of phonemes is. When you talk about looking up whether there is a transition between phonemes or not,
Yes.
where are you looking that up? Because we don't know that.
Okay. So
Like, you have all possible results laid out.
So the inference algorithms for operating on these graphs involve summing over every possible assignment of values to the hidden variables.
Every possible combination?
Every possible combination. If you have a specific assignment of values to the hidden variables, then you can compute the probability of that concrete data case just by going through and multiplying together all the conditional probabilities.
Can you apply the Viterbi principle?
Yes.
You don't have to have an exponential number.
Exactly. Okay. Yeah, so I'm going to skip over other things like trigram language models. Actually, you'll hear about those a little bit later in a talk given by Jerry Torres, one of the undergraduates. And let me just point out a couple of the novel things that you can do once you have this kind of basic structure set up. One of the novel things that you can do is you can express articulatory networks very, very nicely. What I've done here is I've taken the basic training structure that you saw in the first overhead and added a layer of articulatory variables down here. So these might be tongue position and degree of lip rounding. And these are now intermediate between the phone and the observation. So the phone is basically saying, okay, the speaker intends to say th, but, and that would correspond to a certain position for the tongue. But that's going to be, so that gives a target position here, but that's moderated by the previous value of the tongue variable. So that captures inertial effects. And then the observation is conditioned on the articulatory configuration as opposed to the phone that the speaker desires to say. And one other network that we're actually going to see some results for later is a noise clustering network where you basically take the training graph, the simple training graph that I mentioned before, and now you add a new variable that represents a noise condition. The noise condition variable in the simplest case takes a certain value at the beginning of the utterance and is deterministically copied throughout the rest of the utterance. And the probability of an observation then depends on the state, the phone, and the noise condition. Okay, so we've seen all these things that are interesting to do with a graphical model. And in order to actually go off and experiment with these, what we need is a toolkit that enables us to do this. And Jeff is now going to tell us about a toolkit that he and I wrote over the past few months.
Thanks. Okay. To recap, after I get the microphone attached, we've introduced and talked about graphical models. We've talked about the idea of structural discriminability. And we've looked at a number of explicit structures using a graph to represent the kinds of things that we want to use in speech recognition. So all of this would be somewhat moot without the ability to quickly say, we've got one of these graphs, let's get it running quickly. Okay, so GMTK is a tool that allows you to do speech recognition, for example, by specifying structures such as the ones that were described in a graphical model programming language. So basically, it makes it such that it's easy to specify the graph itself, implementation of the dependencies, such as is it a linear dependency, is it a nonlinear dependency, is it discrete, and so on, and the parameters, all in one package together. It's designed and intended for all sorts of large-scale time dynamic problems, such as speech recognition and other time series data, including like genetic data and things like that. We used an alpha version of the toolkit for WS01. It's still in development, and a public release of this toolkit will hopefully be available by the end of the year. It's going to be open source and usable by anyone. And our long-term goal is, again, to have this fully public domain open source version of the toolkit that's high performance, and we are planning to continue to add features over the next n years, depending on how large n is. So I thought it would be interesting, since an HMM is in some ways the simplest graph structure, let's see what an HMM actually looks like in the graphical model language. So we have essentially a string of hidden variables which forms a Markov chain, and then a set of observations, x1, x2, x3, which are, for example, your MMCC vectors at each time frame. So this is what you would type. This is the graphical model language that specifies that particular structure. So let's go at it one frame at a time. So we have a frame 0, And in frame 0, it's basically it's similar to what is normally known in speech recognition as a frame. We have a variable called state. It has a type, which is in this case discrete, hidden, and has a cardinality of 4,000. So in this case, we're talking about a 4,000 state HMM. It has switching parents. By the way, I don't know if people have these handouts or if there are any left, but this, if you can't see it in the back, it's described on page 13, I believe. Sorry, not 13. 14. Okay, so it's on page 14, and you can see it a little bit more clear than what's up on the screen. Okay, so it has a type. It has switching parents, which I'll talk about in a minute, and conditional parents. And because this is frame 0, it has no parents, and it just has a CPT, or a conditional probability table, called pi. So this is similar using the standard HMM notation for the initial state distribution, pi. Then there's a variable called observation. Its type is continuous. It's observed. And it ranges over features 0 through 39. So for example, if you have MFCCs plus their deltas and delta deltas, you would have a 30, well, this is actually 40-dimensional feature vector, so it should be 0 through 38. Has no switching parents again, and its conditional parents are state at the current time using a mixture Gaussians, and a special mapping, a mapping that goes from state to observation. Okay? So that's frame 0. Frame 1 is basically the same thing. The only difference between frame 1, let's go back to this thing. So frame 0 is basically this first stuff without this arrow at the beginning. Frame 1 is the same thing with this arrow. And that arrow is essentially specified by saying, instead of a conditional parents of state 0, sorry, a state saying there are no conditional parents, now state has a conditional parents of state at the previous time frame. So -1 is the previous time frame, using, again, a probability table called transitions. And this is the table that holds what we normally associate as the state transition matrix in an HMM. And then the observation ends up being essentially a rubber stamp of what happened in this case. Okay. All right, so one of the things that I think is novel about GMTK, all right, so there are other graphical model toolkits in the graphical models community. There are a number of things about them that are just not suitable for large-scale and dynamic problems. They're not optimized for speech. Speech is a tough problem, and we have huge data sets. And also speech is inherently dynamic. We needed something that worked on speech, but also had the flexibility of these other toolkits. One of the features that we included in the toolkit is this idea of switching parents, and this ended up being crucial for doing language modeling in graphical models. So the idea of switching parents is somewhat of an amoral concept. So some of you might be familiar with moralization in graphs. There's a concept of moralization, and this is the case when you have multiple sets of parents. So let's say that we have a variable called C, okay? And we decide that we want C to have two parents, a mother and a father. Mother 1 and father 1 are the two parents of child C. But let's suppose that at other times we want C to have two different parents, mother 2 and father 2. Okay? So one thing we could do is we could say, all right, we want C to have two mothers and two fathers at all times. The problem with that is that it increases the size of the table to become a 5-dimensional table, which is, of course, very large. So instead, what we do is we add a special switching parent. And so what C does is C goes and asks its switching parents, okay, who are my parents today? And S says, oh, today your parents are mother 1 and father 1. And then, oh, S is switched now. Oh, sorry, your parents are now mother 2 and father 2. Okay, so depending on the value of S, C will have different parents, either mother 1 and father 1 or mother 2 and father 2. And that's depicted by these bars, so that when S is equal to 0, for example, we choose these parents, and when S is equal to 1, we choose these. And what this has done is reduced a 5-dimensional table down to 2 3-dimensional tables, which is a significant reduction depending on the cardinality of the random variables. It's a significant reduction in number of parameters. Yet we still have this interesting representation where it is possible to specify both sets of parents. How do we do this in a graph? in the graphical model language. So here's a reference picture for the switching guy. We have a variable called S, okay, and it's discrete, hidden with cardinality too, so it's a binary variable. The switching variable itself can have switching parents, but it doesn't. And in this case, it has no conditional parents, and it just has a distribution called pi. And then we define the two sets of parents, mother 1, father 1, mother 2, father 2. And finally, we have the child. And the idea here is that we say we've got switching parents, and the switching parents are S, or is S, using this mapping. And the mapping then maps from values of S down to these two sets of regular parents, mother 1, father 1, mother 2, father 2. Okay. So as you'll see in talks later today, that this, the switching concept was very useful for a number of reasons. Actually, the graphs that we saw before that Jeff showed actually do have switching in them as well. So basically what I've done is blown up one instance of a feature of the toolkit. And it's somewhat arbitrary. There are actually a number of toolkit features that we currently support. So we support EM and GEM training, linear and nonlinear dependencies on observations, arbitrary forms of parameter sharing, so we can tie Gaussians together, tie means together, and so on. We can split Gaussians and banish Gaussians, and so essentially build up a flat start speech recognition system, as you'll see results of. We use decision trees for implementations of dependencies in certain cases, and that's another big memory savings. We also have EM training and decoding again. Well, EM training, that's redundant from here. And we have normal decoding, the standard kinds of things that you see in speech recognition that you were asking about. Sampling, so to generate samples from a graphical model. We have both exact linear space and log space inference procedures so that we can run on machines that has less memory. And finally, we have the switching parent functionality that I described. Question?
Yeah, when do you invoke the switching parent? Is it dynamically through the parties?
So the switching parent is specified in the structure file. So the switching parent is invoked whenever you decide, as a designer of the graph, that you want to have a variable that has different parents at different times. So this was, we can go back. So in this graph in particular, this edge, this guy is really a switching parent of this guy. So that's the way, in the implementations that we show you, this guy ends up being a switching parent. And I think we should, it's fairly complicated, but we should talk about it offline if you're interested. Okay? I mean, in other words, it's not that complicated, but it's something that we should probably save for offline discussion. Okay, so where were we? Okay. So what Jeff is going to talk about next is essentially the first set of results that we got by applying this toolkit on the existing corpora, on the spine, on Aurora, and on the AV, the IBM AV stuff.
I have a question.
Okay.
Clarification as to the switching parent.
Okay.
The way you described it, the switching parent always seems to change the dependency. When you say this arrow going from n-1,
Yeah.
it will go from n-2.
Yep.
But I suppose it's perfectly permissible to say that the arrow will always go from n-1 to C, except that depending on S, you choose two different probability distributions
Absolutely. Yep.
of C given n-1.
Yeah, so we've been calling that, that's a really good question, and we've been calling that switching implementations. So if I wanted to be more precise, I would say that while we use switching parent mechanism above to do that transition variable to the thing, then it's actually a switching implementation in the sense that we're switching from either a copy or to an actual application of the bigram language model, depending on the value of the word transition variable. Okay. Other questions at this juncture about toolkit? Okay, let's hear from Jeff.
Thank you. The pointer? Okay, so we put together this toolkit, and it's time to see if it works. And the answer is yes. And the way that we determined that was to run some benchmark experiments on some of the standard data sets in the industry. So we looked at, the first thing that we looked at was the Aurora data set, which is noisy continuous digits recognition. There's about 4 hours of training data and 2 hours of test data in more or less 70 noise conditions varying according to signal to noise ratio and also the noise type, restaurant versus car versus subway and so forth. And the features that we used for this, we actually used two different feature sets. The first feature set is the standard MFCC delta and double delta features that, that come with the baseline distribution. And the second is a set of features that involve amplitude modulation and frequency modulation analysis, similar to what's done in radios. I'll show some results for those shortly. We looked at the SPINE database. This is a database of noisy defense-related utterances, people saying things that are relevant in battle conditions. There are 10,200 training utterances, about 1,300 test utterances in the data set that we were looking at. And we used a set of features that were provided by OGI, and we also used some Gaussians that Bill Byrne was kind enough to provide for us for comparative purposes. Finally, we looked at the audiovisual data that was used in last year's workshop. This is about 35 hours of training data, 2.5 hours of test data. It consists of simultaneous audio and visual streams, and the feature analysis that was done on it was MFCCs, LDA consisting of the 4 surrounding and following frames, and MLLT. We don't have decoding numbers for the AV data, but we did do a conditional mutual information analysis, and that's quite interesting what we found. So, benchmark accuracies on Aurora. This is showing just absolute numbers, and this is accuracy, not error rate. Down here is noise condition. The noise condition starts at clean, goes to -5 SNR. There are several different test sets, 3 different test sets, and what I'm showing here is just average across all the test sets. The baseline number that we compared to is HTK. It was described in the paper that describes the data set. That's this yellow line here. That's got 546 Gaussians. We created 2 different baseline systems. One of them uses whole word models. That's this blue line here. It does a little bit better than the baseline. And the other one is a phone state baseline that uses the same Gaussians for different phones. And that's this red line. And what you should take away from this graph is that in a relatively short period of time, we took this toolkit, which was basically developed 3.5 months ago, or it's had 3.5 months of development in it, and we're producing these kinds of numbers that are competitive with other numbers. It's got 700 Gaussians, by the way, instead of 546, because we use a Gaussian splitting procedure that splits from 1 Gaussian to 2 to 4, and it happened that we needed 3. Actually, now we've changed the toolkit so that we can get 3, but we didn't have a chance to go back and redo the set of experiments. If you look at the relative word error rate improvements, the graph shows a little bit more. We're doing extremely well under clean conditions with like a 40 or 50% increase or decrease in the error rate. And we have a little bit of trouble in very high signal-to-noise ratios, probably because of the way we're modeling silence. Yeah? Mm-hmm.
What you're describing here is you're just emulating an HMM, so why would the results be better or worse than HGA, which is an HMM?
It's all in the, the number of states that you use, the number of Gaussians. It's just the fine details. So this is showing that you can get the fine details right using the toolkit and actually match baselines. Okay. We also very quickly prototyped a noise clustering system. Karen Levescu is actually responsible for putting that together. She did it extremely quickly. The difference is in the original unnoise clustered system, you had something like this picture that you saw before, the simple training structure. And in the noise clustered one, we just declared an extra variable and conditioned the observation on it and trained a new set of parameters. We divided the noise conditions into two, low noise and high noise. And basically, the system would use one set of Gaussians or another, depending on the exact noise condition. What we found in terms of error rate was that we got improvements in clean conditions and slightly noisy conditions, low noise conditions. It hurt us in the very noisy conditions, and it was intermediate in between. Okay, so we did some analysis of the AM. Yes. Mm-hmm.
The case where you have the noise variable in the model.
Yes.
During training, do you treat that as a hidden variable, or do you actually assign it by hand?
We know what the noise condition is in the training data, so it was supervised clustering.
You could have just ignored it even in training. Right?
We could have ignored it even in training and just learned an unsupervised clustering of the utterances. We didn't do that. We did a supervised clustering. Okay, so we'll be saying a little bit more about results with these AM/FM features later. These are some baseline results. Now, the AM/FM features did not have a discrete cosine transform or mean subtraction applied to them, and not deltas and double deltas either. So they're just very basic features. And what you're seeing here is what happens if you just take very basic features and try to work with them. What you'll see later is what happens if you take very basic features, run the structure induction process, learn an appropriate discriminative structure, and then do training and decoding. If you take the features and just learn one giant full covariance matrix Gaussian per state, you get relatively poor performance. What we then looked at was, let's see, what do we have here? Okay, so the pink line is the AM features alone, learning a single full covariance Gaussian. The blue line that's right under it is the FM features alone, using full covariance Gaussian modeling. And this other line here that is more or less on top of both of those is if you use a block diagonal covariance matrix. So it's modeling both the AM and the FM features with full covariance within them, but no correlations across those two streams. We then did the simplest thing of just concatenating the features to the MFCCs that we had. So if you concatenate the AM features, you get this. And if you concatenate the FM features, you get this. So it's much better because you're using both feature streams. But because there's redundant information and many more parameters, it's actually not doing quite as well as the baseline. And again, this is going to be in contrast to some results that we'll see later with the structure induction procedure. We did some preliminary experiments with spine. It was a little bit more difficult to get fast turnarounds on these experiments because spine is a larger data set and it requires a little bit more care in dealing with it. Basically what we did is we ran a set of noise clustering experiments, supervised again, and we first looked, we built a baseline system doing flat training, so starting with zero means and variances of 1, and we got 35% word error rate. We then tried 6 noise clusters. There were 6 basic conditions that we could identify in the training data, and we trained a system that actually overtrained, and we got worse results. We then combined some of the quieter conditions. There was quiet office and quiet under some different channel conditions. We combined all those into a single cluster to get a 3-cluster system, and that was a little bit better. What this shows is that if you do sort of very brute force, unsupervised stuff, you may not get an improvement, and it's important to try to look into doing discriminative techniques for combining these different for using these different sources of information. For example, well, we'll get into that. And that leads me to the next section, where Thomas will tell us about some of the structure learning heuristics that we're going to use to try to learn better structures to model these things.
Okay, so so far in describing graphical modeling structure, we've been looking at structure over the states. Those are the kind of structures that have been described earlier in the talk by Jeff Films. Now we're going to be talking about ways of using the data to learn structure amongst the observed feature vectors. So if we take a simple HMM model such as this model implies that the feature vector at a particular point in time is independent of all previous feature vectors given the state variable. But we know, and you'll see from plots in a moment, we know that this assumption doesn't hold in the data. And so our goal is to augment the structure of the basic model by adding in additional edges in such a way that we will exploit this dependency that the existing models are ignoring and hopefully improve performance. So as Jeff Films mentioned earlier, we're using something that is called the ear measure. Here, so our goal is, given if we focus on a particular element of the feature vector, we have to decide which of the lagged feature vectors should be assigned as parents of that particular entry in the feature vector. So we have to decide whether to have these two as parents, or to have these two, or we could have 5 parents, or 1 parent, or no parents. We have to make a choice among the subset of potential vertices that could act as parents as to which one is best. And our objective is to, as Jeff mentioned, to increase the expected log posterior. So we want to find a set of parents here which will make the expected log posterior given particular feature as large as possible. And this is equivalent to maximizing the mutual information between the state variable and the particular element of the feature vector given the parents. So you can think of it as we're trying to find parents which are such that they will make the mutual information between the state and that particular element of the feature vector as large as possible. And this is equivalent to maximizing this quantity, where we simply look at the mutual information between the parents that we're considering for a given entry in the feature vector and the feature vector, conditional on the state vector, minus the unconditional mutual information between this vector of parents and this particular entry in the feature vector.
How is that different from just making x of t dependent on x of t I minus 1, completely dependent on it? And how is it different from modeling them jointly?
Sorry, so you're saying how is that different from simply adding, of one thing, we're not considering the parents to be necessarily, there might be no parents in the previous time slice.
Well, but you're considering the possibility of all possible parent structures.
Yes.
So in considering that, isn't that essentially, is that different from just saying you've got a full covariance matrix across, in this case you're showing 3 frames, 3 successive frames. So if you had a full covariance on the 39 times 3 vector, would that be the same thing? It's really quite qualitatively different, because the number of free parameters that we have here, we are simply we are only adding 2 parameters to our model in doing this in this way, because we are first going to select a structure, then having selected the structure, we will then run training and decoding on that new structure. Okay? So the procedure that you're describing will correspond to making the choice that we decide to make all vertices in the previous block parents of x, so that we would increase the number of parameters in a very large way, and we'd have many more parameters to... Okay, so then it would be equivalent to using a full covariance and then just setting all but 2 of them to 0.
Yes.
that you just keep the two biggest ones.
Yes. In addition, remember that these are lagged previously. These are previously lagged vectors. Okay. So one corollary which comes out of our analysis is that that if a set of parents gives an EM measure which is negative, then in general that will not improve our discriminative performance. So we want to restrict attention only to sets of parents that for which the EM measure is positive. So here is kind of the cartoon picture of the way that the structure learning algorithm works. And also this is going to give you a taste of some things you'll see later on in the talk. So we take in mutual information and conditional information, which I'm just representing at the moment by these plots. Later on, it will be explained what these plots are. And we simply do a subtraction, an element by element subtraction of this from this, which gives us this plot here, which is the discriminative information, or the EM measure. And then we for a given feature element in here, we then subtract back across the possible parents, and then we then for every element in the feature vector we then select a set of parents, and this is what's being represented in this graph over here, which you'll see more of in more detail later on in the talk. And just a little bit of notation: when we're talking about parents of observed parent-child relationships between elements of the observed feature vectors, then we often use the term V-link or dependency link. It's just a bit of notation. Okay, so finding the optimal set of parents is hard for a number of reasons. So the first thing that is important to understand is that the EM measure can't be decomposed. So that if you're considering, for example, whether or not to make Z1 and Z2 a parent of X, then Z1 and Z2 have to be considered together, because it's possible that the EM measure for Z1 and Z2 as parents of X is large and positive, so those would be very good parents for X. They would increase our discriminative ability. But either one individually might be 0 or even negative. And so in theory, if we were wanting to find the optimal set of parents, we would have to check through all possible subsets, and so consequently we have to restrict our search in some way. Because were we to check through all possible sets of parents, we would then be looking at 2 to the number of features times the maximum lag allowed for the parent, and that's obviously too large. In addition, even just, for example, evaluating the EM measure for pairs of parents or even just for individual parents, since we've got a large set of potential parents and we've got a large number of features, this is very computationally intensive evaluating this EM measure, and you'll get a flavor for that when you see some of these plots which are showing you the information that we're getting out of this EM measure. So during the short period of the workshop, we in fact restricted ourselves to computing this EM measure on parent sets that were singletons, so sets of parents of size 1. But given more time, there's no reason why we couldn't compute the EM measure for vectors of parents, and Karim will talk about that a little bit later.
Is there any difficulty in adding parents one at a time, really? It seems like Q is already a parent.
Yeah, you certainly could have a procedure in which you sort of found the individual parents that would function best, and then a greedy procedure where you choose one parent and then you then go and consider all possible parents that could operate in conjunction with that. But for example, just computing these singletons on, you'll have to correct me if I get the numbers slightly off, but computing the singleton parents on the Aurora task took us about a week. Is that accurate? A little less, yeah, maybe including restarts. But so consequently, yes. So we could certainly implement a procedure like that, but it might require us another week of. Yeah, you're right. Right. Question.
I have a question about the figure you had on page 24, I guess.
Can you tell me?
No, the following one. Actually, it's the plot, the colorful.
This one, okay.
So here, what you're plotting is you have the different dimensions of x and different dimensions of z, and you're computing the.
I really want to postpone that question to because we're going to have quite detailed description of what these plots are later on in the talk. There's several slides devoted to that, so I will just postpone that.
Okay, I have one other question which is on the following point, which has to do with the ear measure for just z1.
Yep.
So this is the entropy of z1 minus the conditional entropy of z1 given q. Is that what
It's the mutual information between z1 and x given q minus the mutual information between z1 and x.
X is always into the
Yes. Yes. Sorry, I said 4x. I should have subscripted it here, but okay. Okay. So, see, Sanji wants me to speed up. So, what we did in order to evaluate larger sets of parents was we used the following heuristic, which was simply to compute the ear measure for the individual parents. And this is a crude heuristic which gave reasonable performance for when we restricted ourselves to just adding 2 parents. So one thing that we came up against again during the experiments we ran in the workshop was that we had a choice between restricting ourselves to a subclass, e.g. where we had at most 1 or 2 parents, for which we could do the exact calculations and we could find optimal sets of parents, versus being more adventurous and taking some larger class in which we might not be able to evaluate the objective function that we wish to evaluate. We might have to use an approximation. And so it's obviously trivial to see that ideally, if you could find the maximum in the larger class, that's going to be at least as good as the maximum in the smaller class. But given that, for instance, since we had not computed the ear measure for pairs, we only had it for singletons, we were not necessarily evaluating things correctly in the larger class, and so under those circumstances, it's not necessarily clear that you find that among those models that you can evaluate, and given the way that you can evaluate them with limited computational resources, it may not be the case that the best that is found in the large class is better than is at least as good as the best found in the small class. Okay, so I'll quickly summarize. Restricting search to models for which we could evaluate the ear criterion, so in this case where we're adding 1 parent, led to better results in general than approximating the ear criterion when we had many more parents. And so, given additional computational time and resources, we could go ahead and evaluate the ear measure on a larger class of models, including larger sets of parents, and our expectation would be that we would get yet further improvement gains.
Thanks, Thomas. Okay, so the next bit of the talk is going to be about essentially Mukin's question, which was what do those colorful plots mean? What are they actually displaying? And I want to actually just apologize up front because understanding these plots is actually extremely complicated, and it's complicated given an hour, and we have actually less than the amount of allocated time we were thinking we would have. So I'm going to go through them fairly rapidly. But please, if you're interested, ask me afterwards, and we can go through these in much more detail, so you'll know precisely what we're saying. But the basic idea is to understand that just using the ear measure with 1 parent, we obtain essentially a 3-dimensional grid, because we're looking at all of the children here. In this case, we have 6 children, and all of the possible parents. In this case, we have 6 possible parents, but at each possible time lag into the past. So this is really a situation where we have to compute 6 cubed sets of mutual information pairs, both unconditionally and conditionally for each condition. And that's what the ear measure actually requires for the case when there's 1 parent. So this is an example of why it's 3 dimensions, because we have the base position 0, feature number 2. In this case, we have lag position -5, so we're -5 guys over, and it's feature number 4. But think about all possible ways that the tip of this arrow can be on this column, and the base of the arrow can be in any of these guys here. And that's the number of commutations. Yes, Rich?
As I understand what you're saying, given that I'm at a particular state,
Yep.
Looking at feature number 2, whatever my feature vector is, rather than just modeling the density depending on the state, I'd like to say it also depends on some feature value, some dimension of the feature vector, some number of frames ago.
Right.
In time.
That's exactly right.
Wouldn't it always be the case, and you want to find the one that minimizes the entropy or maximizes the likelihood or whatever?
It's, yeah, so that's the key
maximizes
difference.
the discrimination.
Okay.
Wouldn't it always be the case that this feature, certainly ignoring discrimination for the moment, if you're trying to maximize the likelihood or minimize the entropy, you could do that always by looking only one frame back. Any dependence further back than one frame would always be less than looking one frame back.
That is a very good intuition, okay? And it turns out that that's correct as well, that's being a good intuition. So it turns out that pretty much most of the time, if you're only interested in maximizing the likelihood, the best parent to choose for each child is almost always the one just before at the same feature position, okay? However, we have results that Jeff will talk about that show that, actually I'm not sure if they are in the plots. All right, so I don't know if we'll be talking about that, but we have results both that have been done here at the workshop and in the past that show that these are, in some sense, some of the worst parents to choose. These are the ones that do the worst. And you're probably familiar with the autoregressive HMM work that came out in the late 80s and early 90s, and that was originally developed by Alan Poritz in the IDA workshop in 82. And I think that might be an explanation, because while it is likelihood increasing, as you say, it isn't discrimination increasing. Okay? Okay, so we have this three-dimensional plot that we need. So this is an idea of actually what's happening. So I'm going to rush through these, again, I apologize for rushing through these. We have a three-dimensional cube that's indexed on one axis by parent, on one axis by child, and one axis by lag. And for each one of these conditions, for each set of features, we're going to look at the three faces projected down onto each one of these faces. So on the top part of the cube, we're going to project down onto the parent lag axis. The right side of the cube, we're going to project down onto the child lag axis. And in this face, the front face, we're going to project down onto the parent-child axes. Okay. And that's what these things are showing. So the first, and this actually also is very relevant to your question, Rich. So the Aurora phone, we're calling these jet plots, thanks to Eva Holtz, who came up with this creative name for these things, because they look like jet streams. So what we're seeing here is on the left column, the likelihood improving non-discriminative mutual information. And on the right plot, we're looking at the discriminative, the ear measure, essentially, using with one parent. Okay. So again, because we're running out of time, I think there is a main point to these plots, which we get to in the last slide of this segment. Mukund?
Yeah, the ear measure that you had was a function of the Q, right? So if you have a definition plot for each.
So this is a function of capital Q, which is a random variable. So in this particular case, and the things that we're looking at now are the sum, the weighted probability over all Q, weighted by the probability of Q. So it's normal conditional mutual information for the left side of this abstraction. Okay, but that's also a good question. Okay, so let's go through these. This is an example of the ear measure plots when Q corresponds either to a phone for Aurora, or looking at it in the case of a word. And so in some sense, this is looking at the word level discrimination in Aurora. And there are some differences, the main one being that there seems to be a large amount of information closer to lag 0 for this particular feature, which again, because of time, I don't know if we have a chance to go into it.
Jeff, you had an X sub pi, which Thomas did.
Yes, yes.
Which I is.
Okay, so if you're interested in finding, okay. So you're the one with the time plot, Thomas. Chang-Chi. Okay, let's go back to this plot. So we have x sub ti. Okay, so t is, think about t as what's giving us the data. That's the sample data, is over t. I is actually the parent, so I is this axis. So forget about t, think of them as the random variables, and I becomes this parent. Then the different z's become the rest of this cube. Okay?
My question specifically was that if you keep going,
Okay.
so there's this dark red band, let's say the second left.
These guys.
So that corresponds to some 14 or 15 that I'm reading here.
Okay. Yes, so we want explanation on that. Okay. So
is it right to conclude that it's because it's that on the feature vector, it is also the 15th feature? Or is that not true? This could be from
okay, what's happening here is the following. Okay, what this is showing you is for each time lag, the relative value, the discriminative value of each parent. Because this is the parent versus lag. This is showing you for each time lag the relative value of the child. Okay, and in this case, it's basically saying that both the parent and the child at each of these lags are valuable in terms of this measure. And what's actually happening here is when we go back to this plot, it's actually one slice in this cube that when being summarized down either according to the parent axis or to the child axis, it's basically the same, we're getting the same summary because there's a lot of information between the parent and child at that feature in the same position. Okay? And what those features turn out to be, which is interesting, and this will also pan out in the D-link plots that we'll look at a little bit later, are essentially that these are C0 and log energy. So basically, these are showing MFCCs, their deltas, and their double deltas. And this is basically C0 and log energy. And it's saying that there's some discriminative information in C0 about 130 to 150 milliseconds ago. And these are things that aren't really typically seen even in delta features. Okay. I also want to say at this point, I want to thank Eva Holtz for producing these plots. She did a fantastic job in getting these things ready. She'll also be presenting a little bit more work later on. Okay, so now these features are kind of interesting. These are totally different features. They are not MFCCs. These are features that came from IBM, and these are the audio portion of a set of audio-visual features that have undergone a number of different transformations, including maximum likelihood linear transformation, linear discriminant analysis, and a number of other things that Ramesh Gopinath actually did. So what this is showing you is two things. If we look at the non-discriminative versions, there's still a lot of information close in the same feature position. If we look at the discriminative information, you might think, wow, there's a lot of stuff there. But actually, there's actually very little there because it's only the stuff that's most red, because zero unfortunately is very high in these plots. So it's only the stuff that is most red that is discriminative. Like there's a streak there that's discriminative, and there's another one here. So these features have been LDAified. They've undergone a linear discriminant analysis, which is saying that there's a lot. It's removed a lot of, at least from the past 100 milliseconds, which is all we've looked at in these features. Only 100 millisecond time frame. It's removed a lot of the information. Okay. Finally, these are features that we also looked at in terms of they consist of both features inspired by FM and AM communication, and they show you a very different and very interesting picture as well. In particular, there seems to be quite a bit of discriminative information amongst these FM features. So the main zero is about right there. Okay. The main point of showing you all these pictures is that different feature representations of speech probably require a different model. And that if we want to do structured learning, we have to do structured learning not only to the statistics of speech, but to the statistical properties of speech as represented by these features. Okay, so next we're going to have Jeff Zweig again talking about the results of applying the structured learning to these ear measure plots, essentially, to produce results using the toolkit.
Okay, so improved results coming from the use of these procedures. I'm going to show a couple of different things, one for the phone-based Aurora results and another for the Aurora system that used a whole word, a set of whole word models. And we have a number of different plots here that are worth just going through. So first of all, the baseline is down here, and this is a GMTK phone-based baseline that you saw in the first section of the results section. Let's just start up at the top and sort of go down. Okay, so this blue line is with the CAP-Q discriminative measure. So again, that is the weighted average of the ear measure across all the different states in the system. There were 2 links maximum added to the Gaussians in the system. And what you see is a very significant and consistent improvement in the word error rate, hovering around 20%, and going up, especially in the high noise conditions. Okay, well, the first question that you might ask is, well, look, before you had for each Gaussian, for each position in the Gaussian, you had a mean and a variance. So that's 2 parameters. You just added 2 links, so you've doubled the size of your system. You've doubled the number of parameters. Well, how does it compare with the system where you actually go through and just double the size of the parameters, double the number of Gaussians? And that's what this red line is. Basically what we did is we took the original system, did another iteration of splitting to get twice the number of Gaussians. And what you see is that in clean conditions, it's actually a reasonable thing to do. The system can still take advantage of the extra number of Gaussians. But in every other condition, it was worse than doing the discriminative structure induction process. So you can't get away with just taking the system that you have and doubling it in size, especially you're prone to problems in high noise conditions. All right. For comparison, let's see. We've got this yellow line here. This is using the d little q. So here, for each state, we used a set of links that were specific to that state. This is, instead of using the CAP measure, CAP-Q, which gives one structure that is shared across absolutely everything. And that was worse than the CAP-Q result. So this is where the P stands for sharing the structure across all the Gaussians within a phone. The phones in this system were broken up into 3 states, initial, middle, and final. I'm going to refer to that as the phone state system. The green line here is the same d little q for the phone state system, where the d-links are shared across the Gaussians of a specific phone state, but not across all the Gaussians of the whole phone. Finally, you might ask the question, okay, so you're adding links. What happens if I just add links at random? How do I know it has anything to do with this discriminative process of adding links? And what we did here is we added a set of links, 2 links maximum, or 2 links actually, at random for each feature. And that's this purple line. And you can see that it's really not doing very well. So you get a big improvement. It's not just about adding links at random, but doing something intelligent like what's happening in this blue line here. Yeah. Yes?
So the fact that your uppercase Q system, the blue line is up there, whereas the green line is down there, this could say that there are 1 of 2 problems. Either you've learned the structure wrong or you're estimating the parameters wrong. As in not as well, or whatever word you want to use.
Why do you say that?
In principle, I would think little q should do better, right? Because you have a structure that is specific to each state.
We expect that it might, and Thomas has more to say about that.
So that was actually just going back to the previous slide I gave before. The ear measure is giving the correct, is a principal variation of the increase in non-posterior in the case where you're doing the mechanical Q. With little q, you actually should be giving something else instead of the undiscriminated information, which is more complicated and is model dependent. And so consequently, the little q, this is the point I was making, that the little q model is the richer class of models, but it is at the same time 143 and not able to very quickly evaluate performance of a given model. And so it may well be that there's a little Q model which performs much better than the 2 line, but it's hard to find it.
Okay, I thought that the approximation was that for 2 parents you had an approximation.
There are several approximations that
Yeah.
we discussed. I didn't go into this one.
Okay, because the other one also has 2 parents,
Right.
and I thought that may not be. So you're telling me there's another approximation for little q.
Yeah.
And that is what it is.
That's what we're going to do.
Okay, let's go down and continue on with the word-based results. So what we have here is, again, starting at the top, we have these are the results for a whole word state system using CAP-Q and 1 parent maximum. The whole word system was a little bit better to start with. That's this baseline down here. And it's harder to improve on, but we did see something like a 15% relative improvement in the word error rate across all the different noise conditions. Again, you might ask the question, well, what if I just double the number of parameters? What if I just build a bigger system? And what we have here is a larger word-based system with twice the number of Gaussians. And again, although it does a reasonable job in the low noise conditions, when you start to get up to the high noise conditions, it's overtraining and it's just not doing as well as the discriminative methods. We looked at a few different variants. Let's see, the yellow variant is, so the yellow variant. Here what we have is a system that used the AM-FM features, and this was based on a whole word model. The structures, the D-link structures, were tied across all the states in a word, so it's discriminative at the word level. And what we found was that we got a very nice improvement in this case using the AM-FM features. Those are the features that you'll recall that if you just did the simple thing of appending them, you ran into trouble and you weren't doing as well as the baseline. We found that if you are careful about the way that you include different features, that you take advantage of new features that you're adding, then you can in fact produce an improvement in the word error rate. Okay, we looked at also a whole word model using 1 parent maximum in the CAP-Q, and got this red line, again an improvement. And we tried one other experiment, which was to take one of the D-linked structures, one of the structure-induced models, and try to reduce it in size to the size of the original baseline model. That's another way that you can try to get 2 different models that are comparable in terms of the number of parameters. So we removed Gaussians that had low priors and retrained the system, and that produced this green line here, where we took a significant hit in the low noise conditions, but we're still doing fairly well under high noise conditions. I want to also caution that these big jumps under clean conditions are a little bit, you got to be careful about them because there are so few errors in the first place that just a few words difference makes a big jump like this. And if you look sort of at the absolute numbers in terms of some of the better systems that we built, here's the whole word state baseline, the yellow line down here. At the low noise conditions rather, the systems, if you look at a plot like this, are all doing very well and more or less the same. But at the high noise conditions, in the high noise conditions, the structures that we learned are doing better than the baseline. There's a few conclusions that I think you can draw from these, and then I want to point out. The first one is that the result with the AM-FM features shows that GMTK is effectively exploiting novel features in a way that you can't do if you just, for example, append the new features to some old features that you had lying around. Secondly, adding parameters discriminatively outperforms just increasing the number of Gaussians, especially in high noise conditions. and it maintains the results in low noise conditions. Finally, what we found is that in the limited time of the workshop, doing the theoretically correct thing and using the CAP-Q criterion to pick just a single parent works pretty well without tuning. You can basically use it out of the box. Okay, so with that, Jeff is going to show us some analysis of the learned links.
So how many people want to see what links were chosen? Okay, good. That's what you're about to see. Okay, and we're going to conclude at the same time. So the first graph shows essentially just the MFCC system in the whole word state case, when we have whole word systems and we're looking at each state. And we have MFCCs, their deltas, and their delta-deltas. So this also answers one of the questions that were before, which was, what about the autoregressive features, the ones corresponding to the previous guys? So just to let you know what this is actually showing you. So this is showing you the feature position, essentially the position of the child, and this is showing you where it decided that it wants its additional parent in time, going back essentially almost about 150 milliseconds, and showing you which feature it is. So there are 41 features total as labeled. For example, like this guy, which is just C1, says, I want to have C1 11 guys into the past. Okay. Here's that issue with, we're looking at C0 and log energy. There seems to be a strong desire to have C0 and log energy 130 milliseconds into the past for some reason. There are some really interesting, totally cross-stream dependencies that it chose to use. For example, look at some of these delta-delta guys. Like this is delta-delta C, probably 11. It's delta-delta C11, and it's saying that it wants to have C4, 9 frames into the past. There are a lot of these things are here. The delta-deltas are asking for parents 4 frames into the past of the non-delta features, just the plain old MFCCs. So, you know, it's interesting that this structure resulted from the CAP-Q ear measure. It's unfortunately difficult to reason about why is it that these particular links were chosen. We have one strong hypothesis we have is that there's this very strong dependence on C0 and log energy at almost the syllable level. So it seems like something syllabic might be going on in the sense that it's asking for changes in energy at a very long time frame. On the other hand, it's not clear why these are the best dependencies between the delta-deltas and the non-deltas. Okay. So this is an example of the same situation where each child has, rather than one parent, each child has 2 parents. So you can see that the graph gets a little denser, but now we've got an additional feature which is 150 milliseconds into the past. Sorry, an additional parent that's 150 milliseconds into the past. Okay. This is another example of still MFCCs where we are conditioning rather than on the word or the word state, we're conditioning on the phone. So even discriminating at the phone level, it's still wanting to have these C0 and log energy guys 150 milliseconds ago. So this is the example, the very last example that we spoke about earlier, where we're using MFCCs as the children, and we're allowing for MFCCs or these AM/FM features to exist as parents. And the interesting thing is that it's most of the time it's choosing the AM/FM features, and in fact it's choosing quite a large number of, these are the AM features, but it's also choosing a large number of FM features. And again, though, however, it's still wanting to have C0 and log energy in this very long time span. Okay. So I think that should put to rest the notion that it is just the autoregressive or the feature at the previous time frame features which are best. Question?
Doesn't it depend on the size, on the duration of the phone, like if I have a stop constant, that dependency will change too?
Yeah. So that was the difference between the CAP-Q and the lowercase q example, where in the lowercase q we had the dependencies change for each value of Q, whether Q was phone or word or subphone. But as Thomas was saying, we don't have yet the perfect way of computing that lowercase q metric. Okay.
Like if you take lag of 100 units, for a stop constant, it might not be discriminated at all. The same feature because it's of such small duration that.
The issue of might is that this is what the data is telling us, is sort of the globally discriminative dependencies. And if we looked at the lowercase q dependencies for each q, you would start seeing those sorts of issues. Okay. Other questions?
How far back do you go with lag?
We only computed it back to 150 milliseconds ago. So for computational reasons, we didn't compute farther back than that.
If you would done other dependencies back?
I'm sorry, say again?
Did you get a dependency that the maximum you computed?
That's the maximum we computed is, we just stopped computing here.
So it's possible to have gotten longer than?
Yes, yes. In fact, one of the things we'd like to do in the future is go back maybe 500 milliseconds. See what that does. Question?
The question, I guess, is about the baseline model. You talked about phony models, and it looks like you were talking about one state for phony? Or
No, there's 3 states for phony.
3 states for phony. Are they context-independent phony?
They're yeah, they are context independent.
Okay, so, as I'm sure you're familiar, there's a lot of work been done on segment models of different types.
Yep.
And segment models, they all perform very much better than hidden Markov models when using context-independent phony models, usually half the error rate. But of course, the performance level is much worse than with context-dependent models. When you try to use these various segment models with context-dependent models, they usually don't perform better. And the conjecture is that when you have context-independent models, the model of speech is wrong, and very wrong. So modeling the dependency becomes, number one, very important. Number two, you have tons of training because they're context-independent models, so each model has a lot of training, and you can afford to estimate a lot of things. When you go to the context-dependent model, it's a better model, so it's harder to improve because it already depends on states, as you mentioned. It depends on the previous states in some sense, rather than on the previous features.
Okay.
And there isn't enough training data to estimate big models. So I'm wondering if you're sort of repeating that history. Do you believe that when you use these models when you use this approach with models that build in that dependence through context, triphone models or something like that, will you still find this additional information?
Okay. I have 5 answers to that question, and I will give you 2 of them, the top 2. Answer number 1. The idea of structural discriminability is that it pulls out discriminative information where it finds it. If you have context-dependent states that basically indicate that before the current frame you had a P and after the current frame you had a T, or before the current frame you had the sentence, I went to the, and after the current frame you had something else. If we learn to discriminate between these states, if there's no discriminative information there, it should find that, and it should say, sorry, nothing there, no need to add any links. Okay? Second answer. So on some earlier experiments on the phone book corpus, I looked at the improvements in adding these kinds of links for context-dependent models and compared that with any change that might occur in going to context-independent models without links. And going from context-independent models with D-links improved much more than going to context-dependent models. Okay? Which seems to suggest that this was a 4-state per phone case, that 4 states per phone was enough states to essentially get you everything that any context dependence was getting you by modeling it in a hidden variable. And I think the other 3 answers, let's take offline.
I have another answer. If I understood the question, I think this might shed some light on it. We also had a baseline there for whole word models. So there you do have the context dependence that you're talking about. even in the whole word model, we were getting improvement.
Yeah. Right. So
the whole word model perform as well as context-dependent form model.
We didn't make that particular comparison, but I would expect that whole word models, could model all the context within the word.
and that was answer number 4. So answer number 4, another way of stating it, since we're on it anyway, is that what is a whole word state? Okay, that state only exists in that word. It doesn't exist anywhere else. The only thing that that state can model is, I'm the 4th state in an 8-state word. So you are necessarily saying, well, that means that I've came from the beginning of this word and I go on towards the end of the word. So it's a very context-dependent and it's very word-specific variable. Yet we're still getting improvements with this result. Okay? So, all right, good question. All right, so I have to hurry up, which basically means I need to conclude. Okay, so just to summarize what we accomplished. Again, we designed and built a brand new graphical model toolkit for ASR and other large-scale time series modeling. We stress tested the toolkit on 3 speech corpora. We evaluated it with different features. We began improving word error rate results. There are lots of things we want to do. And we started looking at these links across observations. There are a number of things that we want to continue working on, many of which will be described by the student presentations, which will start after the break. Some of which are mutual information and other conditions on other sorts of things like noise type, speaker style, multivariate mutual information, as Thomas was describing, using nonlinear rather than linear dependencies. We didn't really talk about this, but all our dependencies currently are linear. An iterative approach to structure determination, more advanced structures, articulatory, hidden visual, and so on, and discriminative structure learning at the hidden level. And I just want to conclude by, again, thanking everybody on our team. I just want to personally give, you don't clap, I'm clapping for my team. So I want to say thanks, team. I think you guys have been amazing and fantastic. And let's do it again. Okay? So thanks a lot.
Okay, we started 10 minutes late coming in from lunch. We ran 10 minutes over now, so you'll have 10 minutes for coffee instead of 15. And that handout, no matter what it says, is wrong. We don't have a half-hour break. So let's make it 15.